In 8.1, we talked about just very general terms, confidence intervals for proportions and means. And starting at 8.2 and then following at 8.3, we're going to look more specifically at the four-step process. The state plan do conclude that we will be using with very specific types of confidence intervals. So for instance, for 8.2, we are looking at just confidence intervals for one proportion. So I am interested in what proportion of the whole population follows a certain candidate or gets exercise every week or whatever. Some conditions that you need to know whenever you deal with proportions, and this should sound very familiar from Chapter 7, you want your data to be either from a random sample or a randomized experiment, meaning the treatments were randomly assigned. Number 2, you want the distribution to be approximately normal. In order to fulfill this normal condition, you need to have n times p and n times 1 minus p both larger than 10. Now, in sampling distributions, we knew the population parameter, what was true for the proportion of the population, so we used just p. Notice that here, since I don't know what's true about the population, it's what I'm trying to estimate, we just use p hat, meaning the proportion from our sample. Last condition is that the individual observations must be independent. So either state that something is drawn with replacement, or state that if it is a sample, that the sample is no more than 1/10 of the population. Or if it is an experiment, and in some samples, you would just need to state that one result should not affect another result. So in the one that we talked about last class, with the birth rates, that the birth defects, that the birth defect in one pregnant woman should have no effect over whether the next pregnant woman has a birth defect with her baby. An example provided in the book was there's a large bin of beads for which there's an unknown population of red beads. The teacher's class took a simple random sample and got 107 red beads and 144 white beads. So you have the sample, which is randomly selected, and it can be considered independent as long as the sample, which was a total of 251 beads, is less than 1/10 of all the beads in the bin. Okay, if I'm assuming a large bin, then that would be reasonable. And then I have my n, which is 251, times the proportion who are red, which would give you, notice the 251s cancel out, and you're just left with 107. That's greater than 10, and n times 1 minus p, which is 251 times the proportion that it was white, is also greater than 10. Therefore, the distribution of the p hats should be approximately normal. If you would like to stop here and just make sure that you can do one on your own, there is a Check Your Understanding on page 487 of your book, which you can do if you would like, and pause the video. Otherwise, the formula for the confidence interval for proportions, notice that in this case, as I'm talking about proportions, my point estimate is the proportion from the sample plus or minus the z star. Z stars are always used for proportions. We'll talk about how to get that in just a minute, times the standard error of proportions. This is directly from the last chapter when we were doing sampling distributions of proportions. I'm going to flip over here for just a minute to the formula sheet. Notice that the formula sheet says something very, very generic. Confidence interval is the statistic plus or minus the critical value times the standard deviation of the statistic. It does not give you specifically formulas for each individual type of interval. So in this case, our statistic is the p hat plus or minus the z times the standard deviation, and those formulas, standard deviation formulas, are immediately following. So for proportions, we would use this one right here, the root of p hat times 1 minus p hat over n. Okay, now let's talk about real quick how we would find the z. You may have caught on to this, but the z stars that we talk about in class are always directly from this last line on table B. And let me know if you want to see how we come up with that from the original table A, because it is tied to that. But it's this line that says infinity. There's your confidence levels across the bottom, and the number immediately above them is our z star. So if I want a 95% confidence interval, the one that we talked about last time, notice that 95% is actually 1.96 deviations. So when we say 2 deviations for the empirical rule, that's just an estimate. So here are just some practice that we did. 80% confidence would be 1.28 or 1.282. 90% confidence is 1.645, and so on. The notes there below is explaining how we got it from table A, but I just explained it through the shortcut there. Okay, so here's our state, plan, do, conclude. We're going to state the parameter in words. We're going to plan, meaning give the check the conditions. A lot of people also like to put the type of interval that we're going to do in the plan step. Then the do step is where you actually calculate the interval using the formula is how I'd recommend doing it. The calculator shortcut I will show you in a minute as well, and can be used at the very least to check your work. You can do it in the calculator, but there's no way to get partial credit if you do just that without showing the formula. And then the conclusion, we are 95% confident that the interval between blank and blank captures the true proportion, which is the one that we would be dealing with. That's what we talked about last time. So we had the proportion of red beads from Mr. Vigolini's class, and we want to estimate at 90% confidence what the proportion of red beads are in that giant bin. So we have the conditions that we've already checked. There was 107 out of 251 beads that were red, which is about 42.6%. So 0.426 gets replaced for the p-value, the p-hat value, plus or minus the z-star for 90% confidence of 1.645. There's our p-hat and 1 minus p-hat all over the sample size. Calculate it, and you would get between 37.5 and 47.7%. So you would have your conclusion. I am 90% confident that the true proportion of red beads in the container is somewhere between 37.5 and 47.7, or I am 90% confident that the interval between 37.5% and 47.7% captures the true proportion of red beads in the bin. That's just two ways that you can give your answer or your conclusion. Okay. Do keep in mind, this was a caution that the book gives, that the margin of error only includes sampling variability. That's the idea that each time I take a new sample, I will get a different result. It does not accommodate for or eliminate other sources of bias. So if the data were incorrectly calculated or incorrectly gathered, for instance, in convenience and voluntary response samples, it would not help in getting rid of those biases. Now, in the calculator, you can do a 1 proportion z interval. This is kind of the notes on how to do it on the calculator shortcut. We go over to stat and then tests. Okay, so we haven't had to use this before, and either scroll up or scroll down. Alpha A is the 1 proportion z interval. It wants to know how many beads and how many were of the particular color. In this case, there's 107 out of 251 and 90% confidence level. Now notice here my x, this is x, that's how many of the things have the characteristic I'm looking at over the total. Notice it does not want a p, so I don't want to put the 42.6%. I want to put 107 out of 251. Here, hit calculate, and it gives me the same interval that I got from using the formula. It'll be maybe just a few 10,000ths off because we rounded it when we were doing the formula method. Okay, here is a second example. If you want to pause the video here, you can, and try seeing if you can understand the work that was done here. Okay, so the second example in the book, you have over 10,000 college students, almost 11,000 college students surveyed, show that 22.8% engage in binge drinking. Calculate a 99% confidence interval for how many of all college students engage in this behavior. So we're looking for a 99% confidence interval. I wish to estimate at 99% confidence, for instance, for the true proportion of college students who engage in binge drinking. The data does not state that it was from a random sample, So we would have to proceed with caution, or you could even say the random condition is not met. It is still approximately normal because of such a large sample size, so the n times the p and the n times 1 minus p are both greater than 10. Individual observations must be independent, so it is reasonable that the population of all undergraduate students is more than 10 times the sample size, or another way of writing that is that the sample size is no more than 1/10 of all undergrads. The do step, there was 22.8% who fit in that category. The Z star is 2.576 for a 99% confidence level. Plug in the sample size, and this is how you do it in the calculator. Notice that in the 1 proportion Z interval shortcut, the X is the number of students who binge drink out of the 10,904. This is a decimal value. If you type it in, just 0.228 times the 10,904, you need to round that to the next whole number. The calculator does not like decimals in the X value here. Then you would say, I am 99% confident that the true proportion of undergraduates who engage in binge drinking is between 21.8 and 23.8 as proportions, or you can write those as percents. Okay, and just ignore the different wording part. We did not talk about that in class. Okay, so I would recommend at this point pausing the video once again, taking a look at the 8.2 notes, and seeing if you can, or not the notes, the notes that you have printed out, but then take a look at the 8.2 assignment and see if you can get that worked out and checked with the answer key.